Thank you, Rosine, for the introduction and a little bit of the interview. I am Sanyal. I am a PhD student at UT Austin. Today, I'm going to talk a little about how to pre-train with a little less data and compute. So the works that I'm going to show you are jointly done with Atula, John, Abhishek, Professor Alex Dimarkis, and Professor Sujay Sanghvi, who is also my research advisor at UT. Okay, so a little bit about me that I already told you my name. I'm trying to study pre-training and improving the language models with efficient training recipes. That's the direction. By the way, I also stutter a bit, which is natural, so please bear with me. So I have taken a tweet screenshot with permission from a very famous academic, Professor Dimitris Papnipoulos, and a very famous industrial researcher, Dr. Jonathan Frankel. So both of them suggest that pre-training study or pre-training research is in academia is hard. So this, I'm trying to convey the message that studying pre-training in academia is a hard thing. Okay, so here is the outline of the talk. I'm going to talk about the problem setting first, and the problem first, and then the setting. Then I'm going to move to how can we train these language models with a little less compute. Then I'm going to move to the final part of the talk where I would discuss how to pre-train these language models with little less data. Okay, so let's begin with the first section of this talk, which is the problem and the setting. Okay, so as we all know, this pre-training language models is all about data and compute. So I would like to phrase it as the game of data and compute. This compute is measured in terms of flops, which is also a function of the total number of parameters and the data set size, the total number of tokens, which roughly becomes 6 and D based on how they are computed by prior works, and it is also a standard thing now. Okay, so why people are investing so much money in compute and in the data? This is because, as you see, this is all about the scaling law. So the very popular scaling law that came up about language models was Kaplan. He suggested this paper suggested that you can predict the test loss. You can predict the test loss with increase in the number of your tokens and increase in the number of your non-embedding parameters, which would finally increase the total compute. So given more compute and data, you would have a lesser test loss, where lower is better. So they are trying to reduce the test loss with more data and compute, and that's how I told you that this is all about the game of data and compute based on the scaling law. The second scaling law that came into being was Chinchilla, also a very popular paper, which suggests that you need 20x more tokens than the total number of parameters. And both these scaling law papers suggested that you can early stop around 75 to 80% of the training. Okay, so there are a couple of efficient pre-training directions for LLMs, which are mostly popular. I have categorized them in 3 different genres. The first is architectural changes. Sure.
So you talk about both suggested early stopping. I wonder what the rationale there is, because I think in pre-training they just keep the loss just keeps going down. Is it just after a certain point the drop of loss is not even worth it for the amount of compute and data?
So Chinchilla, let me talk about Chinchilla, because Chinchilla was compute optimal. So in a compute optimal setting, given a fixed amount of compute, you can train this much, and that was the rationale. So there is no, so we don't know how far we can train a model which is fully trained. So this typically these language models are trained for one pass of the data, because these data set sizes are like in hundreds of billions or trillions of tokens. So typically, even if you stop a little bit early, it's not considered bad, because if you go beyond you have like, maybe because of the law of diminishing returns, but typically this is what empirically seen as a good advice by many people, but nobody follows it now. Llama and the recent models, they don't follow.
Yeah, I was gonna say, I feel like this has been challenged since that.
Yeah. Chinchilla law and all these laws have been challenged by many different models.
Thank you.
Okay, so the architectural changes to make this pre-training more efficient, there are a couple of recent works, which is in terms of state space models. A famous state space model was Mamba, and then H3, they changed both the attention mechanism and things in the transformer block. So it's a new block for language modeling. So yeah. Then very recently, Google DeepMind came up with this different paper where they showed that RNN-based approaches are not very bad. They, with sufficient amount of compute and data, they can be efficiently trained, and they can have similar performance compared to similar size models of transformer blocks. Then this very recent paper, which came out, I guess, before last week, which shows that if you have a moving average of attention activation as a part of your computing your attention activation mechanism, then then you can have efficient pre-training. This paper is called Megalodon from Meta. People have used all sort of data selection techniques utilizing existing pre-trained models. They have used data like popular techniques like data filtering, the data mixture, and data deduplication. Couple of recent works like Gemini and Llama, given the scale of these models, they have used all sort of parallelism, which is in terms of hardware, model, and data. And some open source language model suite called Pythia has used larger batch sizes. So these are the tricks that people have used to pre-train faster and better, like more efficiently. Okay, now let me come to training with lesser compute. Okay, so let's first see what is the standard language model pre-training setup or procedure. So it's a autoregressive language model pre-training, which typically means this architecture is transformer blocks, we typically decoder style blocks. The loss function is autoregressive, which means negative block likelihood of the next token with respect to conditioned upon the previous token. Typically, most of these papers have used Adam W optimizer. There are the data set consists of hundreds of billions of tokens, now trillions, with from web data set, code, books, papers. So to your right, you could see, you may see a composition diagram of the very popular data set, not very recent, like very popular open source data set consists of like 300 billion tokens, which is like consist of books, web data set, papers, and codes, etc. Wikipedia as well. Okay, so as I were discussing earlier, so large batches of data are fed without repetition. So the standard way, there are a couple of aberrations now, but the standard way used to be, this model has to be fed with large batches of data and for one epoch, which is like without any repetition over the data. Because this data set is so big, like repeating itself would take a lot of more compute. The evaluation, again, is conducted using the negative log likelihood, which is the log perplexity or the val loss on held out unseen data sets. So it's typical like any machine learning setup. There is this downstream evaluation is conducted using some sort of in-context ranking task, some famous task like MMLU. The accuracy and perplexity are the key matrices here. I guess somebody's asking something on the chat, but I would skip it. Yeah, I would. Yeah, I can't see the chat over here. Yeah.
People are discussing. For now, it's okay. People are answering other questions.
Okay, so for this particular section of this talk, we would use GPT-2 models trained on open web text, consist of 9 billion tokens. And then we would also see results with billion-sized Pythia LLMs, which were trained on 207 billion tokens, which are deduplicated. So these are the model configuration of the GPT-2 models, and below are we have four, like 1 billion, 2.8 billion, 6.9 billion, and 12 billion Pythia LLMs. Okay, so let's discuss the recipe first. So what I am proposing, it's like super straightforward, super simple. We pre-train a language model using the standard recipe, which we just discussed. Then we save checkpoints, which are model weights at a given instant I, new steps apart. New steps could be like 10K, 1K, or depending on how much disk space you have, yeah, we can save this checkpoint new steps apart. Then just uniformly average the last K saved checkpoints. We call this specific form of averaging uh, uh, as latest weight averaging, because we are averaging the last K latest checkpoints rather than saving a moving average of the checkpoints. Then we keep on doing the step 2 to step 3 throughout the training, which makes it a tail averaging kind of recipe. So yeah, okay. So what we are doing is we are saving different checkpoints, new steps apart, and then averaging the last K checkpoints. For most of our experiments, we took K is equal to 5 based on the ablation. And we are averaging these checkpoints. Now, an interesting thing which we're gonna discuss further, that we are taking far away checkpoints. It's not like 1K steps apart. We are taking like checkpoints which are reasonably far away checkpoints. So they are not pretty close in their optimization, like in the optimization path. So some prior works in averaging, like in language modeling, nobody uses this kind of or any sort of averaging tricks. But in vision, a small language setting, some people have used EMA in the diffusion model. Uh, they do EMA weights, like EMA weights the downway far away checkpoints. So given you have like far away checkpoints, it will downweigh the weight of that while averaging. There is this stochastic weight averaging, which was again used in a vision language setting, which stops the training at the 75% and then restarts it with a fancy scheduler, and then it selects the checkpoints. It is a little bit tricky to implement. So it's not super straightforward. So these are the averaging baseline which we would consider in this work. Averaging baseline. Then there is there is already the original regular pre-training, which is also the key baseline. Okay, so let's see like why this large batch sizes are used and why large batch sizes requires higher learning rates. So larger batch sizes are typically used to speed up the training of Pythia language models, which is an open source models, and Llama 2 models have used large batch sizes, such as Pythia has used 2 million tokens. Llama 2 models have used 4 million tokens per batch, and they have all used to fasten up the training. And there is a good amount of evidence that if you have larger batch sizes, you need to scale up your learning rates. So this is shown in 2017 by Goel et al. Then also previously, that if you want to scale up the batch sizes, you need some sort of higher learning rates, and it depends the scaling of the learning rate depends on the optimizer that you are using, but that is out of the scope. But you need some sort of scaling up your learning rates. That is all I'm trying to convey. So let's see what if we don't use any sort of scaling. Okay, like let's say we have a large enough batch size and we don't train with higher learning rates, like we don't scale up our learning rates. So what would happen? Okay, so here is the curve to your left. If you see, like with high learning rate, the model loses generalization. So if you don't, if you scale up, sorry, so if you don't follow specific rule of scaling up, like let's say you don't follow the linear scaling rule or you don't follow the square root scaling rule. So if you have a large enough batch size, the batch size remains constant around these models, which is 131K tokens per batch. And you have high learning rates. So we have trained with two learning rates. One is 60-4, which was like researched, and then the other one in green, which is like 10 times higher than that. And you see it loses generalization. And this is the y-axis of the model, which is the validation loss, which lower is better here. And then x-axis, there is the total number of training steps. So let me, sorry. Yeah. So to your right in the plot, we see that if you use some sort of if you don't want to lose on generalization, you can use this latest averaging technique. Even with a higher learning rate, it mimics the path of a lower learning rate, which is 60-4, and then it at the final end, it doesn't lose any generalization. So you don't lose on generalization like you would have if you wouldn't have used any form of averaging. So this is a key thing. If you're using a higher learning rate and you don't know, because grid searching in super large language models is not trivial. It takes a lot of compute. And if you don't want to lose on generalization, then averaging this trick could be useful to you. Okay. So higher learning rate helps LAWA. Everything remains the same. So original means the standard training run. LAWA means when we have added an extra step on top of the standard training run, which I have discussed earlier. Everything remains the same. Validation loss lower is better. X-axis remains the training steps in thousands in K. So as you see that with higher learning rates, LAWA or this averaging techniques, the gains are amplified. So with high learning rates, LAWA helps. Like this specific form of averaging technique helps. Okay. Now you might be wondering like why I'm mentioning like far away checkpoint averaging, So let me discuss a little bit about why early and far checkpoint averaging. Because if you go and read the paper literally says like early weight averaging. So meets high learning rate. So there should be rationale behind it. So why early and why far away checkpointing? So there is an observation that we figured out that these models becomes linear mode connected quite early. And I know this is not the first observation. Prior like Sanyal et al. Has seen this observation in small settings. But as we see in a model that in 10K, after 10K steps, it becomes linear mode connected to a model which is 30K. So by linear mode connectivity, I mean this form of alpha multiplied by the weight plus 1 minus alpha multiplied by some weight, which is like steps apart, like say 10 times steps apart or 20 times steps apart. So if we linearly interpolate these models, we see that these models become linear mode connected quite early, and then this model remains linear mode connected as far as 60K steps, and which typically means we can average these far away checkpoints. These plots are created with Pythia 1B models. So these Pythia models have open sourced their intermediate checkpoints. So that was the thing I used while writing this paper. I have used these open source checkpoints to make these plots. So to run this experiment, I don't have to go back and train these Pythia LLMs. Rather, I have used the open source checkpoints available to me. Okay, so
ask question about the 60K. Which plot shows that 60K after 60K can be averaged?
No, as far as 60K. So the model, the plot to your rightmost, the model weight was 80K, and this model was 140K. So yeah.
Yeah. So where did you draw the conclusion that as far as 60K? Oh,
because it's linear mode connection. Yeah. Far apart means you can have like as good as far as, but it depends on specific models, So yeah.
I see. I thought you meant the training steps going into 60K. No, you mean the two checkpoints that can be as far away as 60K.
Yeah. Training steps going into 10K, as you see this middle plot where there is a model is linear mode connected to a model which is 20K steps apart, and this is like as early as 10K. So this entire model is trained with 141K steps, and as early as 10K, your model gets linear mode connected, which means you can early average. So this intuition might be super simple. I know it's super simplistic, but this is not the way how averaging was conducted in prior baselines, EMA or say this SW, stochastic weight averaging. Yeah.
Yeah.
So that's why it's called early.
Yeah, are these conclusions specific to the GPT-2 and the data you're using and the learning rate, or you think it's pretty general?
So the conclusion with the exact number of step, or this far and this like early and far conclusion, like what can you be specific in this
The
question?
2 bullet points, this as early as 10K and as far apart as 60K.
So as early as 10K, this specific number of steps we have seen in Pythia 1B LLM, which is trained with this pile data set of 207 billion tokens. But I have results I'm going to show you. So this is just the beginning of understanding. I have better results from GPT-2 and Pythia, where I have average checkpoints from 21K steps apart for Pythia, and there is this other setting for GPT-2, and this varies, but these are early, So the core conclusion that I would like to make, again with the support of the next slides, that we can do early and far away checkpoints in many different models. Okay, so let's take a breath here and see what we have just discussed. So the conventional pre-training recipe requires larger batch sizes, which typically implies high learning rates. Since you already have to use a high learning rate LAWA on top of your LAWA, which is latest weight averaging, this specific form of averaging technique, which we are discussing, will anyway help you in your standard pre-training run. And it can be applied early, as Rosine was asking, and you can have far away checkpoint average. So you don't have to store every checkpoint and like out of like GPU disk space or CPU disk memory, disk space. But you can like keep on averaging and deleting this, and since these are far away, you don't have to keep on like storing these checkpoints during your training run. So it's also like helps you in saving your disk space. Okay, so here is the main here is one of the main results. Everything remains the same as we have discussed. Y-axis is validation loss, lower is better. X-axis remains the total number of training steps. We have GPT-2 models, which is small, medium, and large. Let's start with the small model. We can see the green curve, which is the original pre-training curve with a standard setting, as we have discussed. And we have these two baselines, which is the EMA. So typically, any language model training doesn't use averaging. So based on just to make a interesting baseline, we have adapted this EMA and stochastic weight averaging (SWA) for language modeling. So we created this baseline based on their vision implementation, but any form of averaging is not used in current language model pre-training. So as you could see, there is this LAWA hours and then LAWA, which is a little bit far away, far away averaged, where mu is 1K. So as you can see, if you use LAWA with higher learning rates, you get better val loss. Lower is better here, so you gain much more generalization. Your convergence is faster, as you could see here, and it clearly outperforms the regular pre-training and the baseline, which is EMA and SWA. Okay, so this insight remains consistent to the GPT-2 medium-sized model and the GPT-2 large-sized model. So people might be wondering why there is this straight line, like dotted line of 75% training, because this SWA thing is used after 75% of the training. So this is how they design the algorithm, So they apply SWA after 75% of the training. That is where it works. If you apply SWA very early on during training, it diverges. So there is a plot in the paper. I didn't put it here in the appendix, which shows that FWA cannot be applied early on during the training. So that's why I have added this dotted line, which says 75%, because FWA is done at after 75% of when the 75% of the training is finished. Okay, so now let's look into some of the billion size models. As some of you might be wondering, like if this ideas or if this intuition holds in larger size models. So yes, it holds in larger size models as large as a Pythia 1B model. So these are the held out sets from the pile data set, which is philosophy paper, pile book corpus, pile YouTube subtitles. So everything remains the same, which we have discussed earlier. As you see, we win in the intermediate steps. By intermediate steps, I mean that we win not just in the final generalization, which is like lower is better. So we are getting lower word perplexity at the final step, which is 141K step. But we also win intermediately, like intermediate steps. So let's say, as we were discussing earlier, two of the papers suggested that if you want to do compute optimal pre-training, you can early stop. So let's say we stop at 75% of the training, which becomes like which becomes 105K steps. You would get better, you would get lower word perplexity with lesser amount of training steps compared to the original pre-training curve. So this is a very reasonable method to use because you just use on top of your actual pre-training run. But yeah, you have to change your learning rate. But sometimes, like because this model uses like larger batch sizes, which typically uses larger learning rate, so it anyway works. Okay, let's move on to some bigger size, some results with some a little bit bigger.
Pause a bit and for a few questions. People are having questions. I think mostly the previous plots about GPT-2. So are all the runs with the same learning rate, or are llama with bigger learning rates?
No, so the original run was made with this this fine-tuned. So we grid search the best learning rate possible. So this original run and everything is made with the best learning rate possible. The EMA and SWA is ran with the original run, which typically means it's a part of the original run on that particular learning rate. LAWA is trained with a bigger learning rate, like it's a 10 times higher learning rate.
So there's like a potential another curve that's with the higher learning rate, and then the actual improvement of LAWA is over that curve, right? And
yeah, but because in the pre-training, in the previous thing, we have already seen, like if we use the original training curve, like let's say we use the original, we train a model the original way with a higher 10 times higher learning rate, you would lose on generalization. So that would be a little bit unfair baseline to show because we already know that it would perform poorly, you know.
Yeah, so sort of in order to do LAWA, you have to train a bad training because you have to use.
No, it's not. Okay, let me answer this with a specific example. So let's look into this curve, okay? Let's see the fine-tuned or the grid search learning rate is 60 minus 4. So there is this red curve and there is this blue curve with LAWA 60 minus 4. You are anyway getting benefits.
Yeah, that's what I thought. You just take a normal training run that is with whatever learning rate that's best, and then you perform LAWA.
Yeah.
And you said for the GPT-2 curve, you did have to use 10 times the learning rate. So that's where I was confused.
No, 10 times because so 10 we don't have to use, but we have used it because we get higher improvements. This is what we see. And then this idea is to, because we didn't train this Pythia models, so we don't have this control over training this Pythia models. So I think we were compensating there, that we are trying to show as many results possible with GPT-2 so that we can carry it forward to this Pythia LLMs, yeah.
Okay. Some people are asking, why is there like a bump in loss for the first figure, the GPT-2?
Yeah. It's I mean, because it's like there are some people have observed it's called double descent, but that's not the main focus of this topic. So some people have observed double descent like thing in training with yeah. So some people have observed this double descent phenomena, but this is not a main focus of this. This is called double descent. Yeah. If you're asking me why there is a bump, because there is a double descent. Yeah. You would see more bumps because this LLM training is not smooth. So you would see more bumps for following. So yeah, there is this bump with the 6 point. Yeah, there is this bump with this middle plot, which is a plot with 6.9 billion parameters. So the plot to your extreme left is a held out set validation loss, the perplexity with 2.8 billion parameter model. The middle plot is the held out set word perplexity of 6.9 billion parameter model. And then the plot towards your right is the held out set word perplexity computed with the 12 billion parameter Pythia model. So as you see, this 2.8 billion parameter model like performs reasonably similarly with the 1 billion parameter model, which we have seen in the previous slide. Everything here is the same validation set, which is pile philosophy papers, and there are more plots in the paper itself. As you see that in 6.9b model, in 12b model, towards the very end, this two lines like touches upon. So the reason could be this thing, which is this, because to consider like training stability, they have reduced the learning rate sufficiently, so this larger size models, because of training stability reasons, they are trained with reasonably lower learning rates compared to what the other models have been trained on, like the 1 billion or the 2.8 billion models. So this may be a reason, but an interesting thing to look here, that even if you stop, let's say at 75% of the training in the 6.9b model, which is like reasonably large model, you would still get better word perplexity, which is like lower is better. So you would get lower word perplexity with LAWA compared to the original training. So this is yeah, I would like to convey. Okay, so additional result, not the main focus, but this also works in the diffusion model. So my collaborator, Abhishek, he ran this in his Google servers and saw that the diffusion, this LAWA works reasonably well with the diffusion model. And we have this y-axis, which is FID score, where again, lower is better. So we get lower FID with diffusion model as well when compared to the original training. Okay, so previously we have discussed the pre-training val loss. Now let's move our gears to like how does this translate into the downstream evaluation. So I have conducted some small downstream evaluation with GPT-2 models. So I have used 4 different data sets. On an average, a final models checkpoint at 70K steps, because we have pre-trained for 70K, and intermediate I have also a result with 50K. We always win with GPT-2 models. So it's a clear win for all the model sizes at the final step, also as well as the intermediate step. With LAWA, you get higher accuracy. All of these are accuracy, like all the success matrices of these downstream tasks are accuracy. These are ICL tasks which are conducted using zero shot performance, because that's the way how pre-training evaluation on downstream is done. So this is how it is done. So we followed the same methodology. Sorry. Okay. So this is the downstream evaluation of the Pythia LLMs, like billion size LLMs. We see that for 1B and 2B, we clearly have advantage over many different final downstream accuracies, as marked with like bold, the numbers marked in bold. We have a clear win, as well as the intermediate step, because let's say we stopped at 75%, which becomes like 105K step. We also have a clear edge over the original pre-training run, and we don't lose anything. So we are not losing anything with this. For the 6.9B model, for the larger size models, 6.9B and 12B, since the validation loss or the word perplexity there, they have converged. So there is a little final gains. There are final gains, but compared to the small size models, 1B to 2.8B, there are lesser number of wins in terms of final accuracy. But intermediate step, you may observe that in many cases, we have better results compared to the original training done. So the core idea is you are not losing anything. So with 1B and 2B, there is a clear distinction that we are winning with LAWA. With bigger size model, because we cannot retrain this model, given this academic compute I have, like small GPUs things. So I cannot retrain this model with higher learning rate, but the model that we have gotten from Eleuthère AI, which they have trained with reasonably low learning rates for bigger size models due to training stability issues. Yeah. So this is the result we have. Okay, so quickly summarizing, hey Rosin, I have a question. How am I doing in terms of the time?
We have 15 minutes, but we can
Okay.
go if you want. Some people
Okay.
have to leave. But...
Okay, so to summarize very quickly, this latest rate averaging, which is a specific form of checkpoint averaging, is well suited for language model pre-training because you have to use higher batch sizes, which implies higher learning rates. So it could be a natural choice. We can add faraway checkpoints that makes little users, like little lesser usage of your disk space. Then we show that it has clear test generalization benefits and also some benefits in the downstream performance, as shown in the results with GPT-2 and Pythia models. Okay, now let's switch gears and let's talk about how to train small language models. So yeah. So now we come to the section where we discuss how to train with less data, which also anyway translates into compute, but the core idea is to train with less data. Okay, so these are the models, baseline models, which we have considered. As you could see, the MPT, the Pythia, some tiny llama and other models, they are trained for many, some of them are trained for many days, like the tiny llama. They are also trained with extremely large number of GPUs, sometimes TPUs, and they are trained for days. They are trained for, some of them are trained for days. So the idea is, can we pre-train a 1.5 billion model, which is a reasonably small size model, with just one B token, with one GPU, like, because that's the academic, most of the academics have, A6000, which I have in my lab, in half a day, which is less than 12 hours. So this is the challenge that, this is the challenge that we're gonna discuss in the next slides. So the idea is to democratize pre-training, so if somebody can pre-train a small model, like not small, like billion size model, still small compared to like larger LLMs, can we democratize pre-training of LLMs? That's the core goal. And I framed this problem as, is there an easy or cheap way to train a small language model? Okay, so simple and popular directions are using existing models. So people have used like the 5 models are trained with synthetic data generated from an existing model, which is GPT-4. There are data selection techniques we have discussed earlier in the previous slides. Both of them is extremely compute intensive because this larger model has to generate trillions of tokens, which adds to a lot of compute. Knowledge distillation. There are a couple of works in knowledge distillation. Knowledge distillation requires a lot of data, rather the full data of your teacher to be as good as your teacher. Works well in many fine-tuning setup, but most of the times I have seen, I might be wrong, I have seen very rarely that a smaller student is beating the bigger teacher. I have not seen this happening. There could be some cases, but I have not seen. I have not read this. There is this other direction where is pruning. Like if you train large and then compress, there are a couple of structured pruning techniques, like shear llama, as cited here. But pruning also requires a very intelligent technique and lot of GPUs to prune. So pruning is not free lunch. So you have to use a lot of GPUs to even prune a very large model. So it's not like you can do it in one GPU. unstructured sparsity. So pruning leads could also lead to unstructured sparsity, which is not always hardware friendly. So here is this motivation, what we are trying to achieve. So there is this recent paper from Professor Zico Colter's group. It's called mimetic initialization. So they have this cool idea that says pre-training could also be thought of as a transferable knowledge with good initialization. So some sort of benefits that we are getting out of pre-training could be just good initialization. So there is this paper from Microsoft in blue triangle that showed that even with unrelated pre-training, let's say you have pre-trained on an unrelated task, and then you are fine-tuning on some unrelated task, you still get benefits compared to just fine-tuning on a small data set. So pre-training, this actually gives you benefits of good initialization. So as I have discussed, even with zero transferable knowledge, because your domains are different, completely different, you still get benefits out of good initialization. Towards your extreme left, there is this paper that uses zero data, and they have this synthetic initialization technique of the self-attention layers, self-attention heads, which is completely data free. This works well for VITs or like vision setting, but not so good for language models for the reasons they have discussed in the paper. So to your extreme right, there is this world where we need good transferable knowledge with good initialization, which is like almost impossible unless you have the full data set to train your model on. So we want to be in this middle place, this red triangle, where we need some sort of transferable knowledge and good initialization. And by good initialization, I mean I want good initialization of my self-attention layers and FFN, because as you know, a transformer block consists of self-attention and feed-forward layers, which are MLPs. So I need better initialization with some sort of transferable knowledge, not exactly very good. Yeah. So this is this very simple recipe that we saw. So there are two settings we consider: low data regime, and there is the full data regime. So in low data regime, we assume there exists a large pre-trained model, which we consider a reference model with key layers trained with this large model is trained with the train. And there is this small random subset of this D-train, which is publicly available, because as you know, no company releases their models data pre-trained data set. But let's assume we have a super small subset as small as 0.1%. In this talk, we're gonna see a super small subset as small as 0.1%, which is like 1,000 times smaller. So can we develop, we want to develop a scaled down version of a reference model, which is like super large, to a target size model. So can we do it? These are the reference models and some of the baseline models we have used. We have tried to stick to the red pajama or similar domain data set, because if I use something like super out of the box, then we have to see like how the data set is impacting, because data set is also super important. So for the academic purposes, I have chosen small language models in a range of 1 billion to 2 billion size. Model trained on red pajama or similar distribution data. So Pile and this OPT model, the custom data, are similar distribution to red pajama. Okay, so here is this super simple recipe that we see. We take few initial layers of this reference model. Let's say you have a 3 billion model. We take first n layer, let's say half the layers of this 3 billion model, and we retrain this half the layers, the first half, let's say 0 to 13 layers. Let's say this model, this bigger model has 26 layers. We just take the half the layers, which is 13, 0 to 12, and then we retrain it with this small subset of data, which is like super small, 1,000 times smaller, and we retrain it with epochs, like multiple repetitions of this small data. So how far can we go? Okay, so here are the results that I would like to show you with 1 billion tokens. So we have, as we discussed, we trained this 1 billion model out of a 3 billion model with just a random sample of 1 billion tokens. So this larger model was trained on 1 trillion tokens. So we have just a random small subset of 1 billion, which is like 1,000 times smaller. And then we trained this super small model with 1 GPU, less than half an hour, with 1 billion tokens. And as you see, on average of this average downstream score, we took an average of, I'm going to show you in the next slide, we took an average of 9 different data sets and MMLU, because MMLU is super important. We see that we do favorably well compared to the similar size models. So there are similar size models trained from scratch. We are not training from scratch. We have to compensate something with the lack of compute we have, lack of data we have. We are not training from scratch, but we are comparing models which are trained from scratch. This shared llama is not trained from scratch. I'm going to show you. Other models are trained from scratch, and they are trained with 50 to 300 times more data. Okay, so here is this the same plot. This is a more nuanced version of the previous plot with like every like I have highlighted every data set that I have used. So as you can see, I have marked the number in bold where we have at least either 90% accuracy, like 90% close accuracy to the reference model, or this smaller model wins 2 out of 4 models, the same size models. So if we either achieve 90% of the reference model, which is like 2x the size, trained on 1,000 times more data, I have highlighted those numbers. If we or if we win on 2 out of the 4 small size models, which is OPT, Pythia, MPT, and shared llama, I have also highlighted it. So as you see, the MMLU score, because like people nowadays care about MMLU score. So you see the MMLU score is 94% close to the bigger model, 2x the size, 1,000 times more data. And yeah, and on an average, you see that out of like 10 different tasks, we do reasonably well in many different tasks, despite of 1,000 times lesser data compared to the bigger guy or the other models with the similar size, with the similar data set, Red Pajama, or the similar distribution data set. So Pythia and OPT are trained on Pythia is trained on Pile, and OPT was trained on some custom data set, which can be comfortably assumed to be same as Red Pajama. And there is no fancy data selection technique. So we didn't choose best samples. It's just a random subset of 1 billion tokens. Okay, so given more data, intuitively, we would assume to have more, we would assume to have higher score, which this can be seen that these are the intermediate checkpoints, by the way. So if you increase the subset of data, we have previously taken just 1 billion token. Here I have shown 50 billion token result with MMLU score where higher score is better. And then I have shown 3 different reference models. Previously, we have just one reference model, which is OpenLLAMA 3B. Here we have 3 different reference models. But here we don't repeat our token. So we don't repeat with multiple epochs of data. It's just one repetition standard way of just one pass over the 50 billion tokens. And this is how far we can go with more data. There are some discussion in the paper where should we repeat the 1 billion token, or should we just have one full pass of the data, like fresh token versus old token. So I'm not discussing this due to lack of time. This is also super interesting. Some of you might be super interested. I really like this section. Given full data, let's say in a world we have a full availability of a full pre-trained data and the model, which is really available. But let's say in a world where we have the full data and the full big, like the large reference model, can we achieve some benefits? The answer is yes. So now the setting is we have the reference model, we have the full data of the reference model. And now we want to beat the reference model with a target size. Let's say we don't need the full size model, but we want to beat the reference model in terms of val loss, because val loss is used for pre-training. I'm going to show you some results. Okay, yeah. This is Inheritune. This algorithm is called Inheritune version 2. Previously, the first recipe I have shown was version 1 in a setting where we don't have the full data. In a setting where you have the full data, now let me explain you with an example. Let's say there is a 36-layer GPT-2 large model. It is trained for 100K steps, and then we evaluated it on a val set, and we get a benchmark val loss. Then we apply the Inheritune method, reinitialize this 18-layer model with this reference model. Then we train for the same 100K steps and evaluate on val loss, and then see if it matches the val loss or not. Like if it doesn't match or if it's poor than the val loss, then we keep on growing the model. In this experiments, I have grown this model by 2. I'm going to show you the results. So until we achieve, so we take a model, we cut it in half, we retrain with the full data, and we keep on growing the model until we achieve the exact same val loss of the bigger model trained on the same number of training steps, or we beat the bigger model. So either we beat or we match. Okay, here are the results. It should be of interest to you. A GPT-2 large model, which has 36 layers, the smaller guy with just 18 layers, with the same training data, with the same number of training steps, it's beating the bigger guy. This is a little bit interesting to me, but also if you see, there is this other same 18 layer model initialized randomly, even with 2T, like twice the number of training steps, we still beat the same size model, which is 18 layer model, and it beats the bigger guy, which is the 36 layer GPT-2 model trained with the same training steps. So this method can be useful to reduce the model size without compromising your val loss. And it seems this thing translates well to the GPT-2 medium model, where we didn't get the smaller model as half the size, but it's 16 layers. So a 16-layer GPT-2 model, everything remains the same other than the number of layers, achieving the same val loss compared to a 24-layer model. So yeah. So as you see, we can train smaller from the very beginning of training. So this is I'm trying to convey that we can train smaller models, not just pruning. We can train from scratch, because we are training from ground up. So we can train small size model without compromising the val loss. Even the downstream task, because they are kind of the same, the downstream task also remains the same compared to the bigger size model. Okay, so some of you might be curious, like how the training curve looks like. So this is the training curve. The y-axis is the validation loss. The x-axis is the total number of training steps. As you see, the convergence patterns remains kind of the same compared to the bigger model, but now we have the smaller model which outperforms or matches the bigger model. Okay, so a little bit of an analysis. So sorry, Rusen, how much time I have?
We are basically time.
Okay, so very quickly, one super interesting insight. So if you want to initialize like modules of your transformer block, so you should always initialize the attention along with the feed forward network, attention plus MLP. So as you see, we have initialized many different sub blocks of a transformer block, sub modules of a transformer block. So we have initialized the attention module, the MLP module. We have initialized the attention module with the MLP module without the layer norm, because layer norm is parameterized. So the best results we have gotten so far is when we have this form of initialization of Inheritune initialization with larger from the reference model, when you have initialized both the attention and the MLP layers. So this is important, because the previous papers, the prior works, they were mostly initializing the attention the attention heads. Okay, so to quickly summarize, the convention pre-training, as you see, takes a lot of data and a lot of compute. We demonstrated that with this simple and straightforward recipe called Inheritune, we can train smaller language models with very limited data and compute. This could be our recipe may help in democratization of pre-training for small language models to people who does not have like a lot of compute resources. Let's say we have the full pre-training data, Inheritune still works and it outperforms the bigger model, and it helps to decide the sufficient depth of a model. So as you see, a GPT-2 large model has 36 layers, and we have the same VAL loss of a smaller model with 18 layers. So now we can safely assume that the smaller 18-layer model, 18 layers can be a sufficient depth to achieve a particular VAL loss. So with Inheritune helps in both setting, which is low data regime and full data regime. Thank you very much for listening and attending this talk. Feel free to read the paper attached, and also the code is publicly available.
Okay, I don't know how many are around for questions. Let's stop recording and do some question.